Hey class, Mr. Bean here for AP Physics. This is video 12, Gravitation Part 3 for AP Physics 2020. All right, so we're still continuing our talk on gravitation, and this time we want to talk a little bit about orbits and stuff, and just some little background information here, and then we'll get started here. So while back, something you may or may not know here, that take a look at this figure number 14.3 here, says if you throw a stone at any speed and 1 second later it would have fallen about 5 meters below from where it would have been without gravity. Okay, this is a fact about gravity. Okay, it falls about 5 feet for a second. Okay, after 1 second of time elapsed, it's 5 meters. How far it goes depends upon your initial velocity. Okay, now this interesting fact here is that the geometric fact about the curvature of our Earth is that the surface drops a vertical distance of nearly 5 meters for every 8,000 meters tangent to its surface as shown in the figure here. Okay, so over here it says a 5 meter drop for each 8,000 meter tangent means that if you were floating in a calm ocean, you'd be able to see only the top of a 5 meter mast on a boat 8,000 meters away. All right. So what does that mean? That means if you're in the International Space Station here, okay, for every second, okay, take a quick look here. That means if you can go this distance, if you can go 8,000 meters this way, you will have fallen 5 meters this way. If you can do that, you will have a circular orbit around the Earth. If you can maintain 8,000 meters in this direction by 5 meters down, you will have completed a orbit around the Earth. Okay. Now, what does that mean? Okay, or how do we come up with that? So this is what's called Newton's canon. So let's go over and take a look at Newton's canon here, and we'll start off at a very low velocity. So in this here, this is an imaginary mountain far above the atmosphere. And here you are. Okay, and here it says for low speeds, the cannonball doesn't get far relative to Earth's size. For the downward gravity gives a parabolic path. At higher speeds, the cannonball goes far enough that the direction of gravity always points towards the center of the Earth. Okay, changes. So does the shape of the path. All right, so take a look at this and see what that means. So we're going to fire this at 2,000 meters per second, and let's go and trace the path and see what happens. Okay, so let's go maybe 3,000 meters per second. Well, not much further. Okay, let's go like 4,000 meters per second. A little bit further. Okay, let's go like 5,000 meters per second, or 5,050 meters per second. Okay, let's go about 5,900 meters per second. Okay, get a little bit further. And 6,550. Okay, let's go about 6,850. Okay, getting there. How about 7,100? All right. Hey. Okay. Okay. All right. So if you go fast enough, you'll be able to maintain circular orbit. Okay. All right. So that's what this whole discussion here is about. So you may want to do some more reading here. And here it says astronauts in a space shuttle are not weightless. They're actually in free fall. Okay. So you're in free fall. Okay. So go ahead and read about this. This is good article here. Okay. All right, here's question 816. It kind of talks a little bit about gravity and finding what the acceleration due to gravity is. So here it's saying that a space shuttle orbits the Earth at about 380 kilometers. What is the gravitational field strength due to the Earth at this altitude? So the mass of the Earth is 5.98 times 10 to the 24 kilograms, and here's the radius of the Earth. Now, remember, when we do this problem here, remember, this is big G here, right? Okay. Okay, so in order to solve this problem here, we have to use this equation here. So we're going to use mass of the Earth, big G, and R. Now remember, R has to be the radius of the Earth plus the altitude. Okay, a lot of people forget this and get things wrong. So when you're at this altitude, the effective G is only 8.75 meters per second as opposed to 9.8 meters per second. Okay, so something to think about. All right, so here's another problem here. Here's 817. Now here's the solution here, but I'm gonna go ahead and kind of show you how we would do this. Okay, so here's this, here's mass 2 and here's mass 1, okay? And this is giving us the orbital radius here. And of course, the force of gravity is acting this way. So the force of gravity is providing the centripetal force here. So how we would do this is we go like this. Force of gravity, right, is going to equal, is going to be supplying the centripetal force. Okay, so the force of gravity is big G, right? This will be mass of the Earth. Okay, and here we'll call this the mass of the Earth here. Okay, and M2 will be the mass of the satellite. Okay, so mass of the Earth, mass of the satellite divided by R squared. Okay, so it's from the center here to the center of this satellite. That has to equal centripetal force, which we know is M, mass of the satellite. Okay, this is the mass of the satellite here, times V squared over R, like so. Okay, all right. So this is what gravitational universal force is, and this is centripetal force. We can see here that the mass of satellites cancel out, as does one of the R's. So what happens is that we have big G. Here's mass of the Earth right here, right? Divided by R is equal to V squared. So for velocity for an orbiting satellite then becomes V is equal to the square root of, this would be G here, mass of the Earth like so, all this divided by R. So this is an equation for circular orbit. And remember, we also have V is also equal to 2 pi R, right, over T. So we can't forget this as well. So this still comes along, and this is new. Okay, so this is the speed for circular orbit. Okay, circular orbit. All right, has it worked out over here? Now, next thing I want to talk about is what's called geosynchronous orbit. Okay, it means a satellite maintains an orbit which has a period of 1 day. Okay, geostationary orbits are orbits directly above the equator. Okay, so just keep that in mind here. Okay, so geosynchronous orbit means that the period is, we'll say what, 24 hours, right? 24 hours, or it's in SI units, it'll be 86,000 right here, right? 86,400 seconds. Okay, so we'll keep that in mind right here. 86,400 seconds. Okay. All right. So here's some other problems in here for you to look at and some questions here. Okay. Now here is escape velocity. Okay. Now we'll talk more about it when we get into energy, but let's just do a quick comparison here. So velocity for circular orbit, take a look here, is big G, the mass of the Earth here, divided by R. Okay. Now, when we get into energy, next unit we'll talk about where this equation comes about. But let's just say that velocity to escape here, take a look at it here. It says it's the square root of 2 times G times M times R. So I'm going to go ahead and pull out the square root of 2 here. And we have here G M1 divided by R, like so. Okay, and so what happens then is that, or mass of the Earth here, like so. So this becomes square root of 2 times the orbital velocity. Okay, this is the orbital speed here. So what that ends up being then is this is approximately 1.41 times v. So if you can go 1.41 times the speed of the maintain circular orbit, you'll have a sufficient velocity to escape and leave the orbit. Okay. All right. Here are some questions here real quick here. Here we have the diagram below represents 2 satellites of equal mass. A and B are in circular orbits around the planet. Okay, and then here it says compared to the magnitude of the gravitational force of attraction between satellite A and the planet, and the magnitude of the gravitational force of attraction between a satellite B and the planet is what? Okay, uh, now I'll give you some hints about this. Okay, think about this relationship here: 1 over r squared. Okay, all right, so this is talking about the gravitational force of attraction. So consider this. I mean, you could think about G is equal to big G mass of the planet divided by r squared. But really, it only deals with this fact right here. So we'll hit pause and we'll let you do it. All right, we're almost finished here. We'll let you go ahead and take a look at 8.21. Take a look at this problem here, and here's the solution here. Okay, you hit pause and take a look at that. And then finally, the last thing we'll talk about here is video 12, finding the mass of an orbiting body. Okay, finding the mass of orbiting body. So let's go ahead and see what that's all about. All right, so let me go ahead and get thing here. Let me go ahead and get the Earth here. Let me just go with shapes here. All right, so let's go ahead and get like the. So here's like the Earth. Okay, it's nearly. So we'll see. We'll assume it's circular. Okay, now over here we'll do another circle, and we'll pretend that this is like. Let's say this is the Moon. Okay, so we have the Earth and the Moon here, and let's go ahead and go back to drawing, and let's say it's moving in this direction here. Okay, so this will be the mass of the Earth here. Here's mass of the Earth, and this here will be the mass of the Moon. Okay, it could be a satellite or, but it's just something circling a central body. Okay, now from here to here, we have this is the radius of the Earth, right? Here's the radius of the Earth, and this here, we'll call this the radius of the Moon, right here, right? Radius of the Moon, and in between here, we have some distance, d. Okay, so off to the side here, I'm going to say that big R is going to be the radius of the Earth plus the distance in between and plus the radius of the Moon. Okay, that'll be big R. That will just kind of help us out here. All right, so so what's keeping this to go in a circular motion around the Earth here? Okay, is the force of gravity. So we could say that now we make a couple assumptions. Mass of the Earth is much, much bigger than the mass of the Moon. Okay, or generally speaking, for this to work, this has to be much, much bigger than the mass here. Now, matter of fact, instead of calling this the Moon, let's go ahead and pretend like it's a satellite. Okay, well, I like that better. It's a satellite. Okay, because the moon is, it's I mean, it's smaller than the Earth, but it's not maybe small enough. So we'll pretend that the mass of the Earth is much, much bigger than the mass of a satellite. All right. So what we have here then is that the force of gravity is here. Here's the force of gravity, and that's got to equal the force of centripetal force here. All right. So the question is, what's the mass of the Earth? Okay. How do we know what the mass of the Earth is? Okay. Because there's not a big scale in outer space. How do we know? Mass of the Earth. What is it? All right. So we'll go over here. And here we have big G, of course. We have the mass of the Earth. And we have the mass of the satellite. Okay. All this divided by r squared. Okay. Remember, it's not the moon, it's a satellite. That has to equal centripetal force, which is m, we'll say here, v squared over r. Okay. All right. So when we do this here, this is mass of the satellite. These cancel out, as we can see here. This is r, that cancels out, and that cancels out. So let's go ahead and go, here's big G. Here's mass of the Earth here. All this here divided by r. Okay. Equals v squared. Okay. Now, off to the side here, right? Off to the side here wasn't v, because it's nearly circular. 2 pi r over the period, right? And therefore, v squared equals what? 4 pi squared r squared over t squared. Okay, so that's what v squared is right here. So we're going to take this here and I'm going to substitute it into here. And let's see what happens here. So we get here big G, here's mass, big G here, mass of the Earth over R, right, equals, now over here, this was v squared, right? So it's going to be 4 pi 4 pi squared. Here's r squared all over t squared. Okay, now we want to find the mass of the Earth, right? So here's mass of the Earth. It's going to equal, now I got to be careful now. This is going to be 4 pi squared. This is going to be r cubed. R's don't cancel, it's r cubed divided by. So but g would be over here, and this will be t squared. All right, so let's kind of rearrange it a little bit here. Let's get all the constants together. So there's 4 pi squared over g is right here. Okay, and over here, we're going to have r cubed all over t squared. Okay, so this is r cubed over t squared. Yeah, that looks terrible. This is r cubed over t squared. So this is how we find the mass of the Earth. Okay, and it's 4 pi squared over g. We have to know how far away it is and also the period. If we know this information here, we can find the mass of the central object. All right, that will conclude video 3.